today we're going to learn how the simple integration, the thing that I taught you yesterday, and the thing with which I bored you yesterday, how it works in the code. Let me just make this thing proper. Okay, so as I said, any machine learning model or any machine learning program, you have to start with NumPy, Pandas, Matplotlib, and Seaborn. It's like default. If you don't want to show your machine learning model how it looks or how it like the visualization, you can remove Matplotlib and Seaborn. But you should have Pandas and NumPy. Without that, you cannot start any machine learning code. And I guess this is the first machine learning code I'm explaining, so listen to it properly. So we have Pandas, NumPy, Matplotlib, and Seaborn. Now, the very first the very first time I'm showing you the Sklearn library. What Sklearn library is? Sklearn stands for scikit-learn. Scikit-learn library has almost all the machine learning model algorithms predefined. You do not have to write the whole code. The things I explained yesterday about simple integration, that all those mathematical formulas, all the gradient descent thing, you do not have to write it by yourself. You just have to use the functions which are provided in scikit-learn. Like it's completely programmed and it's completely there. You just have to write the code. You have to just call the function, and it's gonna do all the things for you just by we're gonna go over linear regression. So what we did, sklearn.linear model. You have to find out in which particular patch your algorithm is. So that's not a thing that you have to remember about. You can just Google it, like where exactly the linear regression model stands. So from sklearn.linear model, you have to import linear regression. And we take one more thing, train test split. What this train test split does is, this function just gonna take the whole data from data frame, and it's gonna split the data into training data and testing data. Because you do not want to do like, you can do like take 0 to 2000, like you have 10 rows. You can take like 0 to 7 as a training data, 7 to 10 as a testing data, and save it in another data frame. You can do manually also, that's not a big deal. But train test split is a function which does it for you automatically in a random fashion. So it's not going to take 0 to 7 only. It can like pick 1 or 2 in between somewhere, and give you the output. So it's a efficient way of splitting the data into training and testing. Now, and the third library which we're using is from Sklearn, import matrices. Matrices is model evaluation matrices, like the model that you made, how accurate it is. There are like so many functions which you can find out, with which you can compare a model, like which model is better, the first one or the second one. So there are different kind of matrices that you can use. They're like mean squared error, absolute mean error, root mean squared error. We'll look at that in some time. Now this thing is done. Now we input a data set, weather.csv. Now weather.csv has 1,19,040 rows and 31 columns. As you can see, it's a big data set. Now the columns which you have is STA, the date, the precipitation, wind gun speed, maximum temperature, minimum temperature, mean temperature, and so many stuff are there. So we took this data set. Now we describe the data set just to see what all stuff are there. So we can have the count of the STA, the mean, standard deviation, 25, 50, 75. These things are not going to be useful right now because we know what exactly we're going to do. And we're going to make a simple linear regression line. But when you're working, like as a professional, when you're working, you have to go through this describe function a whole lot to find out what exact machine learning model you're going to put, because they don't tell you what exact machine learning machine learning model you have to put. You just have to decide on yourself, and it should be accurate. Now, today I'm going to take variables, maximum temperature and minimum temperature. As I said, simple linear regression will take only two attributes. One will be the dependent, one will be the independent. So we took minimum temperature and maximum temperature. So x will be the minimum temperature, which will be the dependent one. Y will be the x will be the minimum temperature, independent one, and y will be the maximum temperature, the dependent one. Now we plotted this graph, minimum temperature to maximum temperature with dataset.plot. Now I told you about all the scatter type graph which you can make using plt.scatter, like matplotlib.scatter, but even dataset like the pandas dataset has their own function of plot. So we can write the dataset name dot plot, provide the x value and the y value and the style with which you want to show your data points. I said O, so it's gonna use O. If I put star, it's gonna give star. If it's dash, it's gonna give dash for all the data sets. Now, the title which we gave is filter title, min max temp, x label is minimum temperature, y label is maximum temperature. As you can see, the data set that we have is some kind of a linear line. It's like a baseball bat, but that's what you guess on. That is the linear line. So what does the data suggest you? The data is telling if the maximum temperature, as you can see, if the minimum temperature is higher, the maximum temperature is higher. If the maximum temperature is higher, the minimum temperature. It's like a linear combination. Like the more one thing is higher, the other thing is also that much high only. So that's kind of obvious. If the maximum temperature is high up for a particular day, the maximum minimum temperature will also be high for that particular day. Unless and until you are living in Sahara Desert or something where you have extreme climates. So now we showed you data. Now we search for the distance plot. Like out of what data, out of all the data that you had for max temperature, at which range it has the maximum amount of occurrences. Now we put plt.figure is 1510. Now this particular plt.figure, in that figure you can put so many stuff like how big your graph should look like, or what kind of color you can just describe in this figure only. Now we use fig size. What fig size takes is it takes the height and the width and plots you the graph that particular height. Provided 15 to 10, so the graph is bigger. If I'll small it to 5 into 5, you will get a square which is smaller than this. Now we use the C-bond distance plot, this SNS, the C-bond. We use the distance plot, and we plotted the distance plot as it is. Now you can see the distance plot of max temperature is there. So you can see from 0 till whatever. Oh, sorry, it's minus 20, 0, 20, 40 or something. Now you can see out of all the data that you have in maximum temperature, most of the data lies between the scale 20 to 40. Now this is one information that we can use if we do not know the model which we are going to use. Currently, we know that we are going to use the simple linear regression because the chapter is simple linear regression. Looking at this and getting the information will not be really useful right now. But just to let you know that you can find out different information. What happens, Seva? Nothing. Okay, so you can find different information, and using that you can come to your own conclusion that which model you're going to use. So we can see from this particular line, with this particular function, that most of the data in maximum temperature lies between 20 to 40. Now, what we did is we made our input x and y. Now we took the data set min temperature dot values. Dot values gives you the values inside the data set of this min temperature. Now, why we did the reshape? If I'll show you, okay, let me just come here. And execute everything from starting. Yeah, executing. So what is till the time I'll say what exactly reshape is. Reshape, as you remember, what does reshape do? It's just going to reshape your data that you have into the particular format that you want it to be. Now, do I connect to the internet? Yes, I'm connected to the internet. It's taking some of the time. Okay, let it take some time. So what does reshape will do? It's going to reshape your exact data set, like data that you're providing into -1 to 1. Now, what is -1 to 1? You're not providing exact length and breadth. So what does -1 to 1 does is it's going to let the data that you have. It's not going to change the data set shape in anyhow. It's just going to provide one. What can you say? One dummy column, so that okay, it's executed. Now where's the function? If I'll show this line executed, I'll show this line executed. Now reshape is there. I make one more line. Copy. Copy. Paste. Now I am taking x the data shape dot values. Exactly the same. But if you'll try to find out what is the shape of that x, so we'll go for x dot shape. No, sorry, capital X. Capital X. We'll go for capital X. Now we can see it has 1,19,040 rows, but they're not showing any columns. It means it's just standalone rows, nothing else. But what linear regression function has is it will take a 2D array. It will not take a 1D array. It's how the linear regression function is defined, that it will take a 2D array. So we should have single column, that it should show that we have this much number of rows and one column having this data. So that's why I use dot reshape. Reshape of -1 to 1. What it does is it just provides you a small like what a dummy column, so that it will make you'll make it compatible to the function that you're going to use. Because if you'll print the x value without the reshape, you'll print the x value with the reshape, the exact same data you'll get. But just to make it compatible to the machine or the, I guess now you know the example of reshape. Now the train test split, the best part. Now what we do is we use this function train test split. We provided the x values and the y values that we got from this data set. The x value is the minimum temperature, y value is the maximum temperature. We made the test size as 0.2. It shows what percentage of the whole data you want it to be the test size. So I gave test size as 0.2. It means out of all the data that you gave, 20% will be the test size and 80% will be on the training. So your model will train on the training data, which is the 80% of the data, and it will try on testing on the 20% of data. Why we are scrapping the 20% of test data from here only, that we can figure out that, okay, we have two kind of testing data. One has no answer, like we do not have any answer of that. Like we're literally testing on it on new unknown data. We don't know that data. Even we don't know the answer that it's going to be accurate or not. And in this particular test data, we know the answer because we put it out from the main data set only. So we know the exact answer, what the answer should be, and then we'll try out. And we know the answer, but we didn't train the model on that particular points. We know the answer because of the training, because of the data set, but we didn't train on that because the training will only happen on the training side, not the testing side of this data. Xtrain and Y-train will only help in the training, not X-text and Y-text. So we know the answer, but the model is not trained on that. For the model, it will consider it as the unknown data. So then we can accurately find out what is our error, because there are chances like if we do the overfitting of data and we try to test on data on the training data the data on which we trained on, it's gonna give some random results. Like it will give you like perfectly 100% results, but on unknown data it can just go crazy. So that's why we split some percentage of test data also. And random state none. Random state none gives you what? If you let random state none, so every time you run this line, you'll get a different set of training data and testing data, because random state what this function does is it's not gonna like split the data in. Okay, it's just gonna split the whole data set into first 80% is the training and the second 20% is the testing. It's just going to take random values in between and then they give you. So if random state is none, so every time you include the execute this particular line, it's going to take the random values from anywhere. But if you put random state 1, it means every time it's going to take that exact random point each and every time. So each and every time your answer will never change. If you put random state 2, it will make 2 random steps and you're gonna get one of the random steps. If you make random state 3, they'll make 3 random steps and you're gonna have only one of the 3 random steps. 3 random steps. So that's training and testing data. Now you did all the stuff. You check your data. You made the data compatible to the machine. You started the training and testing. Sorry, you split the data into training and testing data. Now the main part, the linear regression. And how much time it took you? This particular 2 lines. We made linear regression we call the linear regression function and made a whole, what it's called. We made call the linear regression function and saved this object in a word called regressor. You can use any variable name you like. Now, fit function. Now, all the function that you have in the machine learning model, or all the function that you have in scikit-learn, will have this particular function which is called fit. What does fit does is it's going to take your training data and start training a model on the training data that you provided. So what we give the training data itself. So regressor dot fit. We provide the X train and the Y training data. So the X column of the training data and the Y column, the answer of the training data we provided. Simple as that. So it's gonna give you one line like how it's working. Now, after executing this line, your model is trained. Now you'll know, as I explained to you yesterday, the simple linear regression tries to find a line y is equal to mx plus c. Out of all the data points that you're given, they'll try to find a line y is equal to mx plus c. So what exactly the model has to find? You'll give them the y is the answer, x you'll give them to guess. You find what? M and c. It means what? You find the intercept and the coefficient. And just to get to know what is the intercept and what is the coefficient, we have a particular function, regressor.intercept underscore. It will give you the intercept value, which is 10. To find the coefficient value, we have regressor.coef underscore. It's give you the coefficient value. So it means the line that you created will be y is equal to 0.91 something 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 x plus 10.117981. So that is a particular line that your model made and says that this is the best fit line for your whole data set. Now, how to predict the model? To predict the model, like to give you the data and like you provided the data and you want the machine to answer that data, answer that inputs with the output of the output. The machine thinks that that's the right answer. So we use regression dot predict. Predict function will take the input, just the input, not the answer that you're providing. You just give them the input and it will give you the exact answer like what machine think that should be the right answer. So we did what? Regressor.predict. We provided the testing data and we got an answer in the y predicted. Like the answer relative to the test data, what is the predicted answer with the predicted answer from the model? Now, what we did, we know the exact answer because the testing data is obtained from the main data frame only, and we have the predicted data that the model predicted giving the data set of testing of x. Now we're going to print both of them. So tf is equal to tf of data frame. We made a data frame of actual, and in actual we give the y test flatten. Now flatten does what? If you'll even if you'll remove flatten, it's not going to be effective. It's not going to affect here right now. But I'll tell you what flatten does is, just imagine you have a 2D array 1, 2, 3, 4, or a 3D array like 1, 2, 3, 4, 5, 6, 7, 8, 9. Flatten does what? It's going to take the whole data and just flat it in a single one-dimensional way. Just imagine 1, 2, 3, 4 are there. It's going to take the whole data and it'll like 1, 2, 3, 4, like a single line. It's going to make it a 1D array of whatever thing you gave it. It's going to make a 1D array to that. That's what I call a flattening it. So we did the flatten just to be extra cautious. Now actual is equal to y test of flatten, and predicted is what the model predicted, y predicted dot flatten, and we printed it out. So for all the data for which the model predict actual is this particular values and the predicted is this particular value. As you can see, for x is for the first try, this is not giving the value of x, by the way. This is the row numbers. So for the first x value, the actual answer is 29.444. The predicted is 29.073. Kind of similar. Second one, 32.777. Predicted is 32.644. So they are kind of similar. For some of them, you will find out there's a huge gap. Like for the fourth value, the answer is 30.000. The answer that you got from the model is 33 point something. So there's a huge gap. So that's how you get the answer. Now, just to make it more visually attractive, what we did is we plotted a graph. We plotted a bar chart to be exactly. Plotted what kind, which is bar chart. Bar chart. Fig size is 1610. We provide the major, Major just stands for like the proper lines, which are like, you can see this green lines. You can have the major grid lines if you want to see. Now we provide the line width and the color green and show the graph. So what showing? The yellow line shows the predicted value for each and every value of x, and the blue line shows the actual values of x. So you can see for all the combinations, the actual and the predicted are somewhat similar. For some there are like big differences, for some there are not. So that's what the answer is. Now we want to see the exact line, how the exact line looks. So what we did is we took the x text, we started the plotting the line. How we plot the line? Making the plotted line using exact dots. So first we put the scatter plot, that what point should be there. So we made the color gray and started putting the x text to y test. So these are the testing points, the exact testing answers. Now we plot the exact line, what the machine thought of the answer should be. X test to y predicted. So these red lines are the y predicted lines. This is the exact line that our machine made. Y is equal to mx plus c. This is a particular line. Now we want to see the matrices. So we can use the mean absolute error, mean squared error, or root mean squared error. Mean absolute error will do what? For each and every predicted value and the actual value, it will take the distance, add it for each and every value. That's mean absolute error. Mean squared error, take the distance of the actual and the predicted, add it, take the distance, then they'll square it, as I said yesterday about the mean squared error. They'll square the value and they'll start adding it. That's mean squared error. Now what is root mean squared error? As the name suggests, take the distance, it will square it, it will add all together and make a root of it. That's root mean squared error. As you can see, all the answers that you have got, the mean absolute error is 3 point something, mean squared error is 17.53, root mean squared error is 4.1. So these are the errors. So we'll make 2 or 3 more models of that, and you can see that for one model your mean squared error is 4. For the other model that you made, your mean squared error is 3. So you can say that the other model is far more better than this particular model. So this is your linear regression. Now for multiple linear regression, I'm not going to explain you again multiple linear regression because it is exactly the same. You don't even use any other function. It's exactly the linear regression. That's it. You do the exact same thing. The only thing you cannot do here is to plot the graph, because I'll show you. That time the input that you have is a single feature, which is the min temperature or the max temperature. Here we have so many features which are as input. As I'll show you, the data set that we had is the wine data set for the wine quality. So the fixed acidity, volatile acidity, citric acid, residuals, so many stuff are there. And then you get the quality answer. Like what is the quality answer? 5, 0, 3, something like that. Now, what we did is we did the exact same thing. We did nothing else. No, but what we did for the splitting of data, like how we're going to make our x and y. For the data set of x, which is the input value, which is the training data, we didn't take only one value because it's a multiple linear regression. So we can have multiple input values. As you remember, for simple linear regression, we have the line y is equal to mx plus c. But for this one, you'll have y is equal to m1x1, m2x2, m13x3, and so much and so on. So we took how many functions? Fixed acidity, volatile acidity, citric acid, residual acid, chlorides, free sulfur. Like we took, I guess, everything. And y is the answer of the quality. So we're trying to find out from this model, what is the effect of all this fixed acidity, volatile acidity, citric acid? What is the effect of all this particular feature on the answer, which is the quality? So we made x and y. If I try to find out the shape, 11 columns of H shape, fine enough. Now, I'm not explaining this because the distance plot is not going to be useful for this particular program also, but I just made it. Now, do the same thing, x train, x test, y train, y test. Provided the x and y value. Again, did the x test testing size is 2, 0.2, it means only 20% will be the testing size. Random state is 0. For this random state 0, every time I'll run this code, I'll get the exact same answer. I'll get the exact same splitting. So the output will be exactly the same. But the previous one which I showed, because it's known, every time I'll run the code, every time I'll get different values for the line will be somewhat different because the data set which we provided will be kind of different. So every time we'll get a different kind of like slightly different answers. Okay, so linear regression, we made the regressor file, regressor.fit, we provided x train and the y train. exactly the same. Now, in that particular time, we use the coefficient array. We could use the coefficient function, and it gave you the only one answer because coefficient was only one. Y is equal to mx plus c. We have only one m as the coefficient. But in this, it has m1x1, m2x2, m3x3. So it's gonna give you so many numbers of m. So the type of regressor coef will give you a numpy array. And if I'll show you what exactly regressor coef gave. Okay, for that I have to run the code from starting. So you can see the regressor coefficient gives you the coefficient value of each and every attribute that you provided. As you can see, the provided are fixed acidity, volatile acidity, citric acid. So for each and every one, respectively, it gave you the coefficient. This is the first fixed acidity. This is the citric one. This is that one. Like this is the fixed. This is the volatile. So to make it like look at more attractive, you can see fixed acidity got the fixed acidity and got their coefficient as 0.07. Volatile has got this 0 minus 1.31. So this is the line that we made. Y is equal to this much into fixed acidity, this much into volatile acidity, this much into this much into this, and you'll again execute the intercept underscore. You'll get the intercept, the last constant value. That's it. Now again, we'll do the prediction thing. We predicted the value. Now the data frame that you want to see for the actual and the predicted one, and we'll plot the graph. So now we can see that's the same exact graph. We made the bar chart in a different fixed size to provide the major lines, which is just the grid lines. Line style is dash, line width is 0.5. So this is just the grid lines. If I'll remove this particular line from here, just to show you, this is some kind of a, you will not have the grid lines. That's it, nothing else. Just to make it look more attractive, we made the grid lines. Now you can see the predicted and the actual are somewhat similar, and there are some cases in which they oscillate way too much, like you can see here. That's it. In that code, I showed you the line visually, but you cannot do it here because we have so many different attributes. If we have 3 attributes, we can use a 3D diagram, but we have like 7 to 8 attributes. It means we cannot make a 7D or 8D diagram here. So we cannot show it in we cannot show it in visualization form. But we can again find the absolute mean absolute error, mean squared error, and root mean squared error. We executed it. Now the answer that we got. The mean absolute error is 0.56. The mean squared error is 0.53. The root mean squared error is 0.73. You can see simple integration has really high error values 3. So the mean squared is 17. Root mean squared is 4. But for multiple integration, the squared error is really less, 0.7, 0.5, 0.53. So you can find like instead of giving only one column as a feature and getting the output is less accurate as compared to giving all the columns as their features and getting the output. And that doesn't say that you can just give all the values, all the features. You have to find out which feature will affect. There are some chances in which the feature will never affect the feature that you're providing for the training. It's never going to affect the model anyway, but you're providing it. It's gonna just make your model worse. So you have to decide what exact model, like what is exact feature you want to give to the model to train. That's multiple and simple integration code. I'll send you these two integration files, see to it. And again, I'll suggest go through the video which I sent yesterday again, and again read the code. You will have whole clarity of all the things that you wanna know in multiple and simple integration. Time is less than 1 minute. The class is over. If you have any doubt, text me in the group or put it in Slack or do whatever you want. Okay.